for coming, so today we have Niloufar from France to talk about drawing, right? Please.
Thank you. So thank you for inviting me. Today I'm going to talk about, the title is cross-cap drawings and sign reversal distance. So the first thing, cross-cap drawings are something that is related to graphs embedded on surfaces and graph drawings, but the second one is a notion in computational biology. So I'm going to tell you how these two are kind of related. So this is joint work with Arnaud de Mesnay and Alfred Aubin, who are my ex-supervisors. And please feel free to ask any questions anywhere it was not clear. You should stop me and ask. So I'm going to start with a Mobius band. So what is a Mobius band? Is a surface that we obtain after, imagine that you have a strip of paper, you're going to twist it and then attach the two sides together. So let's see if I can use this. No. So for example here, I'm going to do this.
Yeah.
So this is a strip of paper and I'm going to attach the two sides with the directions that I've shown here. And the surface that I'm going to get is something like this, which is called a Mobius band. Now, what are the things about Mobius band? So it's very interesting because it has only one side, meaning that, for example, if you consider this cockroach that is walking on it, it would see all of it with continuously walking. And the other thing about it is that the right and left on this band are not well defined, which is, what does it mean? So for example, what the cockroach sees at the top at its right, it's going to be at its left after walking once along the string. Okay? So this is the easiest example of a non-orientable surface, which are the things that most of my talk would be about. Okay? So now let me tell you about a similar twist in biology, in genome rearrangements, to be more specific. So you know that a DNA is something like this. It's made of nucleotides, and segments of DNAs are called genes. Okay. Now, in the 20th century, biologists discovered something quite nice. They were studying the genomics of some species, and they found out that some of them, the difference in some of them is not related to the type of the genes, but just the order of the genes, like the sequence of the genes. So here, for example, I am encoding let me try again. So here I'm encoding the genes by the numbers, signed numbers, and the top one is the genome of cabbage, and the second one is a turnip. They have the same type, but different order. So this led to this, they decided to somehow study the evolutionary distance between these type of genomics. Like for example, they were considering some mutations, and they want to know what's the minimum number of these mutations that you need, for example, to change cabbage to turnip. So the mutation that I'm going to talk about is called a reversal, and what is it? So I'm just going to look at the sequence of subsequence. I'm going to reverse the order and the signs. So for example, here -5, -4, -3, -2 becomes 2, 3, 4, 5. And as you can see, to turn cabbage to turnip by reversals, you just need 3 reversals. Okay?
So you reverse sign and also permute?
Yes, yes. So if you just consider it as this arrows, then it's just completely mirror.
So do you distinguish between the 1, 2, 3, 4, 5 and the -5, -4, etc. lead to -1?
Yes. Let's say yes. Okay. So now this twist kind of is very similar to the Mobius band, as you can see, for example, here. For example, if I have this WLF walking on my Mobius band, when they come back at the other side, they will be FLW with this reverse. Okay, so we can kind of look at these reversals like Mobius bands. Someday I'm gonna explain more, and in the whole talk I want to use this similarity and explain to you how this led to solving 2 problems. Okay. Any questions so far? Okay. So let's do some introduction. So I'm pretty sure everyone knows, but I'm just going to explain in case there is someone who doesn't know. So a surface is just a topological space that locally looks like a plane, which means that if you have any point, sorry. Okay, now it's good. Okay. So if you have a point and you look at like small neighborhood around it, either you have a disk like this that looks like a plane, or for example like this, you have a half plane, a half disk, and anything that has these properties is a surface. Now the points that have the set of points that look like a half circle around them, they would be the boundary of our surface. Okay, and these are, for example, some examples for surfaces. And a surface is called non-orientable if it contains a Mobius band in it. For example, this one is the Klein model, and it is non-orientable, and you can see this in this blue colored thing, the Mobius band, and here is where the twist is happening. Okay. Otherwise, it's orientable. For example, the first three surfaces are orientable here. Now, I consider the surfaces up to homeomorphism. So, a homeomorphism is just a continuous bijection from one surface to the other one, in which the bijection is also continuous. And informally, you can just look at it like you can continuously deform one to the other one without gluing or cutting. So that's it. So I would, if two surfaces had a homeomorphism between them, they're homeomorphic. They're the same to me. Okay. Now let's talk about type of curves that I can have on my. Oh, I'm so sorry. This is not the one. Wait, sorry. Yes. So not type of curves. So one way that you can consider all these surfaces is to like make them from a sphere. So you can have a sphere, you can cut some disk like this, and either attach a handle or a Mobius band. So here this boundary of this handle is getting attached to this one, and Mobius band has only one boundary, and I'm just, it's a circle, I'm going to attach it here. In the case that I'm only attaching handles, I'm going to get an orientable surface. And as soon as I have one Mobius band, then my surface is not orientable. And the thing after attaching Mobius bands, I'm gonna depict it with something like this, which is called a crosscut. There is a weird crossing happening because non-orientable surfaces are not embeddable in 3D. So, and okay, in the orientable case, the number of handles are the genus. Here, the number of Mobius bands are the genus. So I'm going to use this kind of representation a lot. And there is a nice theorem that says that all surfaces can be classified by their genus, the number of boundaries, and their orientability. Okay? So now let's do the type of curves on surfaces. So first, what do I mean by type of curves? So I mean a homeomorphism type, meaning that if I have two curves, for which there is a homeomorphism of the surface that maps this one curve to the other one, these two curves have the same type, okay? Okay, now for example, let's consider an orientable example with this double torus. So a curve is separating if it cuts the surface into two connected components. For example, this red one, when I cut the surface along it, I get these two. And also, I can have this kind of separating. So when I'm cutting along these blue ones, I'm getting a disc and this one, right? So in this case, I'm just going to call it a contractible, separating that is contractible, and this one is a separating non-contractible curve, okay? And these two are different with the type. There is no homeomorphism that is mapping these two to each other. There is another type of curve on this here, like these two green ones. So these two green ones are actually having the same type, okay? So if I cut along any of them, I get this surface. So I can define the homeomorphism between the two shapes, and that's it. So in this double torus, I have three types of curves, okay? Now, the case is a little bit more complicated for non-orientable ones. So here, for example, is a non-orientable surface. I have different I have separating and contractible and these things, but my non-contractibles are a little bit more different. So for example, a curve is one-sided if it has a neighborhood that is homeomorphic to a Mobius span, and is two-sided if it has a neighborhood homeomorphic to an analysis. For example, here, this pink curve has a neighborhood homeomorphic to a Mobius span, but this one has a neighborhood homeomorphic to an analysis. Okay, so these two are different curves. So let's look at this one. So here, for example, B is a separating that is not contractible. When you cut along it, you get this surface. A is a two-sided non-contractible. When you cut along it, you have this. You somehow kill the handle here. And C, when you cut along C, you end up with one boundary, and kind of you killed one of the cross gaps. Okay? But the most interesting part is the curve D, because when I cut along this one, I suddenly end up with something that is orientable. Somehow this one is killing both of my cross gaps. So these kind of curves are called orienting, and it's different than the other two. So an orienting curve can be one-sided or two-sided depending on the genus, but it's a different curve. Okay? And these are actually very useful because we know a lot of things about orientable surfaces that could be generalized if you just take the orienting, cut your surface into something orientable, and use the result that you know for orientable ones. Okay. Now, let's. Okay, the surfaces that I'm working with are kind of in a discrete model. So they are made with polygonal disks attached to each other. For example, this double torus that is made with like small triangles. You can also see this as a graph that is embedded on this surface, and in which an embedding is just an injective map from the graph to the surface. Okay, and like embedded graphs in general are useful, like for like graphics, like for example this dragon or these weird road structures. So nice thing about embedded graphs is just they somehow give your surface a discrete metric. So what does it mean? So imagine again that my surface is this triangulated double torus that is like the graph of the triangulation is giving it a metric. The curves that I'm allowed to draw on this are curves that are crossing the edges of my triangulation, only transversely, okay? And now the length of this curve would be the number of times that it's crossing these edges of this triangulation. So this is the metric. Any questions? No? No. So I have a simple question for you. So I have these two surfaces. One is like it's made with 3 cross gaps, and one is with one handle and 1 cross gap. Do you think these two surfaces are different or the same?
Same.
Okay, good. Everyone agree? Okay. So, do you know how to show the homeomorphism between these two? Okay, so one easy way to do this. Oh, for those who don't know, I should say that a handle in the presence of a cross gap would count as 2 cross gaps. So these two are the same, indeed. And one way to do this, to somehow compute the homeomorphism between these two, is to cut both of them into a disk. So for example, the left one, I'm cutting along this graph that you're seeing. I get a disk with this ordering around. And for this one, it's a little bit more complicated, and I get this. After this, you can use the homeomorphism between these two disks and then glue up the whole surface. But for these to work, you really need the disk that you get to have the same form, right? You want to be AA, BB, CC, something similar. So you have to cut along the same shape. Now this is what I call a decomposition of the surface or of the graph. And one natural question here is that how much can we control the length of the decomposition? So if my surface is given like a discretely with some graphs on it, how much can I control this length? Okay, this for the rest of the talk, let me tell you.
Length is what? The number of sides of that polygon?
What?
What is the length?
What is the length? So here my surfaces are, it's not a good picture. Imagine that the whole surface is triangulated.
Yeah.
And then the length is that, as I said before,
Okay,
the curves are only allowed to cross the
Okay.
edges of my graph transversely, and the number of crossings are the length. So, sorry.
number of crossings. Okay.
Yes. So let me tell you what I'm going to tell you in the rest of the talk. So the first thing that you're going to see are two main technical tools. The first one is it is a model to represent graphs embedded on non-orientable surfaces, which is called cross-cap drawings. Yeah. And the second one is an algorithm from genome rearrangement, the sign reversal distance, the title of the talk. So, and then I'm gonna talk about the first problem regarding decompositions, short decompositions for non-orientable surfaces, and then degenerate crossing number and Mohar's conjecture. These are the two problems that I use the two tools to solve. Okay. Now let's start. Okay, sorry, I should have done that. Two technical tools. So the first one is cross-cap drawings. So this is a very nice model to somehow show the graph that is embedded on a non-orientable surface. So let's say my surface is this before attaching the Mobius spans. So these are three boundaries on my sphere, and I am attaching these three Mobius spans to it. For example, here the blue part is attached. This blue part is getting attached to blue part, and the red to the red. Now, imagine that I have such a curve that is entering in this blue part. It goes here, it comes out of the red part, and continues here. If I have another curve right now that somehow starts at the right of this black one, it goes there, it comes out from the red one, and it ends up on the other side of the black. So this is how the Mobius span would react to this kind of curves. And now I can have like multiple edges. I can continue it even to a graph. And this is a graph embedded on a non-orientable surface of genus 3. But as you can see, the information that I have at the top are kind of useless, so I can forget.
Cancel.
So,
Can you press the cancel?
So you said all faces are this, right?
what?
So what you can graph on purposes means that all faces are this.
Yes, yeah, the embeddings that I consider like that. So the information at the top are kind of useless, so I can forget about it, and I just can look at this. I'm gonna replace the boundaries like this. I'm gonna call these things again cross-caps, and even the sphere is a bit too much. So this is a cross-cap drawing that represents a non-orientable embedding. And one thing that is important is that this is not kind of canonical. For one embedding, you can have different kind of cross-cap drawings. For example, these two are the same embedding, are the same embedding, but the cross-cap drawings are two different. So, for example, the blue here is just using these cross-caps, each of them once, but here it uses this one once, but 2 times, and once. So, this is the main tool. And one natural question again here is that how much can you, when you are computing such a cross-cap drawing, how much can you control the number of times an edge is going into a cross-cap? This would reduce the complexity, right? The complexity of your drawing if you can control it. And the best thing that we know so far is a theorem by Schaefer and Stefankovic. It's a very nice algorithm, weird algorithm, that given any embedding of a graph on a non-orientable surface, it computes a cross-cap drawing in which every edge enters each cross-cap at most twice. So we know that we can do it at most twice, but we don't know if we can do it at most once. Okay? So any questions? Okay. So I'm gonna move to the second tool, which is the genome rearrangement. The problem that the evolution thing that I explained at the very beginning can be turned into a computational problem. It's called sign reversal distance, where you just consider two sign permutations, where a sign permutation is just a permutation in which you can like give the elements can be negative or positive. And then you want to compute the minimum number of reversals that you go from one of them to the other. So for example, here, go from A, B, C, D, E to this one. And here, these are the reversals that we show. And there is a, surprisingly, because in this computational geometry, there are not so many efficient algorithms, but this one, surprisingly, has a polynomial time algorithm by Hannan-Halley and Pevsner. And again, I can show you that this has a lot of similarity. If I just associate a strand to each of my letters, then the reversals become like cross caps. So let me do this multiple times. So then I can, for example, I drag everything to one vertex, and this is a graph, and this is a cross cap drawing, right? So this is the relation that I'm going to use. Now I think I'm ready to. Are there any questions? Because I'm going to start with the first problem.
In triangulation, you use just implicit triangulation, or you may admit some quotienting like delta complex, something like that.
I didn't understand.
I mean, in torus, you can decompose like two triangles if we admit quotienting, and in this, I don't remember, 10, 8, much more triangle when we triangulate, implicit triangulation. So in your
well,
setting.
I'm not sure if I understand, but let's talk after.
Yeah.
Maybe. Sorry.
So can I add to this? Probably I don't understand the meaning of the line arrangements for the cross-cap drawing.
This one?
Yes. So for example, like, okay, so we do not think about the cross-cap inside in there, but by just looking at those lines, we somehow know that there is a cross-cap there. Is it correct? So that is what I don't understand, because I don't know how using those lines that we know that there is a cross-cap.
Okay, so do you mean how, I mean, not the picture, if I'm given with this such a graph,
Yes,
how do
yes.
I know to add the cross cap there?
Yeah, right.
Okay, so this is not that easy, but you're gonna see.
Okay.
Okay, so let's continue. So the first thing I'm going to talk about is short topological decompositions for non-orientable surfaces. So decompositions, I already told you. So we before my work, we knew that any orientable surface somehow could be cut efficiently to such along such a decomposition. This one is called an orientable canonical decomposition, and it is the one that when you look at the order of the edges around this vertex, you see AB, AB, CD, CD, okay? Something like that, or A1, B1. And when you cut this double torus along this, you get a disk with the same kind of ordering A, B, A bar, B bar, C, D, C bar. So these kind of decomposition were known. There is a theorem by Lazarus, Paciola, Wechter, and Beust that given any graph that is embeddable on an orientable surface, you can always compute such a decomposition such that every loop of this decomposition processes each edge of the graph at most 4 times. So it's constant, and the total length of the decomposition would be order of Gn. So this is considered quite short. But what about non-orientable surface?
What do you mean by loop? Loop?
So loop is just for any edge of the decomposition.
Actually, what do you mean by n?
N is the number of edges of the the metric, the
Okay.
graph of the metric.
Okay.
So for example, the edges of the triangulation here.
Thank you.
Yeah, and G is the genus of the surface. Sorry, I should have said that. Okay, so
the total length just follows from the claim that each edge is cross each loop crosses each edge at least 4 times. Hence, well, no, it's, yeah.
So
just
here
one.
it's once, I think.
Here's once.
Here
yeah.
it's once, yes.
Yeah.
But in general, for any
Yeah,
embedding,
yeah.
it's
So GN you get like
yes.
4 times something. How many loops do you need for a graph of genus?
It's order of G.
Is this one typed?
Hmm?
Is this typed in this case? Is this factor 4 avoidable?
No, I don't think so. It's not. Nothing is typed.
Okay.
So it means that if you get those loops or those decompositions, then it is not easy to reduce the number of crossings to by 1. So
You mean like
for
making it
each
three?
edge.
I think this is the best. That so far that we know. I'm not sure if you can do. I don't know.
So it is very different.
Yep. So now, for orientable surfaces, this result was known, but nobody cared about non-orientable surfaces except me. So that's why we studied this problem. So a non-orientable canonical decomposition is actually the one that you already saw. Is the one that around the vertex you see the edges like with this order A, A, B, B, C, C. Okay, and when you cut along it, you get this kind of polygon. And so this is our result. We prove that if any graph is embedded on a non-orientable surface, you can compute a canonical non-orientable decomposition in which every loop is crossing every edge at most 30 times. So it's a little bit too much, but we don't care because it's constant and it gives us order of Gn, and we're happy about it. So this is a matching bound with the previous one. The best known bound before this was order of G squared n, which was using the same approach for the orientable case. But since the non-orientable ones are like the approach is by using the cut and pasting algorithm of the classification theorem. But for non-orientable surfaces, it was giving an overbound G squared. So now what we do is that we use a new approach using the algorithm of Schaefer and Stefankovic for cross-cut drawings and the Hanen-Halley-Pesner algorithm from the biology, computational biology. So now, before going to explain like sketching the proof and everything, let's talk about the conjecture that is somehow asking about a more general question, like other decompositions. So there is a Negami conjecture that says that if you are given two graphs G1 and G2 embeddable on the same surface, can you embed them simultaneously at the same time on this surface such that each pair of their edges cross as most a constant number of times? So this has been open for a long time. It was the main topic of my PhD, but it's still open. So if this is true, then you can just fix one of these graphs as the graph of the metric and the other one as some kind of decomposition, and would somehow imply that every decomposition can be computed with total length that was order of n1 and 2, where n1 is the is the number of edges of the graph of the metric, and n2 is the decomposition. So so far, I think we don't know even many examples that matches this bound. The canonical decompositions for both orientable and our result for non-orientable matches this bound. It gives order of Gn, where it's good. Okay. And okay, regarding this conjecture, what the best thing that we know is by Negami himself, that says order of G crossings between each pair of edges would be enough. But this is a little bit too much for us. Okay? So let's move toward the proof somehow. So in these kind of questions, one thing that is like pretty useful to like somehow make the problem easier is to contract the spanning tree. So let's say this is, for example, this is, if you glue the red and green edges, this is a torus and graph embedded on a torus. And I can reduce this by just contracting this yellow, the graph with the yellow edges. And then I would end up with a one vertex graph. This is much easier to work with. Why? Because the whole embedding then can be encoded with very little pieces of data, which is the order of edges around the vertex for orientable ones. And for non-orientable, you just have to put a sign for each of them. the signs would correspond to the sidedness of that loop. Okay, so for 1 here is for two-sided loops, and -1 is for one-sided. And now sketch of the proof. So I use Schaefer and Stefankovic algorithm. So we know that using this algorithm, I can always get a cross-gap drawing in which every edge enters each cross-gap at most twice, right? So let's say I've given my example to this algorithm, and now what does it mean? That it means that if I look at these small curves here around my cross gaps, then these are crossed by the edges of my graphs at most twice each, right? If I had a way to somehow find these paths from each cross gap to a certain point, and somehow make sure that these paths are like not that long, then I could make these kind of curves by following the path, going inside the cross gap, go around it, and going back. And if you look at this, the order of edges around this, it would be A, A, B, B, C, C, and that's my decomposition, right? This would cut, this would solve the problem. So the whole thing now is reduced to somehow control the diameter of this drawing that I'm going to get from algorithm of Schaefer and Stefankovic, okay? Okay, I'm gonna explain like roughly how this is done. So let me tell you how the algorithm works. So the algorithm is by induction. At each step, they deal with one type of curve, different types of curve. For example, I'm going to explain to you the case where they are dealing with a one-sided non-oriented loop. Let's say R is such a curve. Then they're going to remove R. They're going to look at this wedge. They're going to reverse the whole thing like this, even the signatures. Okay. And by induction, they know that they can draw this with some cross gaps. And to get back R, they just cut these ones from here, the ones that they reversed. They add a cross gap, they pass through everything through it, and they draw R. Okay, so this is how the algorithm works. Now, what I do is that we build a system of short paths from every cross gap that this algorithm adds at each point to a certain point. Like for example, let's say I'm going to fix this point, and I want to somehow make sure that all the cross gaps that this algorithm is adding is not far from this one. So the algorithm has some freedom that I'm going to use. For example, here when I have this R and I wanted to remove it, I could reverse this one or this wedge, like two wedges. So let's say I'm going to reverse the wedge that does not contain my point. And then let's say that in the induction, I know that there is a path from every cross gap to this point. And when I'm adding this new cross gap, I'm not changing the length of any of the paths that I had by the induction. And for the new one, I just have to go around the vertex. So it's not that much. Are there any questions? Okay. So the algorithm, so we somehow modify their algorithm and use the freedom to make these paths, but it's not as easy as I just explained. Not every step is that easy. There is a step that deals with separating non-contractible ones, and in this one, so it does this thing. So they have a separating curve, which here is this loop S, the green one. So they separate the graph to two parts. By induction, they draw both of them, and they want to attach, right? In some cases, there is a problem because the number of cross gaps that you use at the top and the number of cross gaps that you use at the bottom would not add up to the right number of cross gaps. You might have an additional cross gap here that you have to get rid of. So what do? They do a very strange move to remove one cross gap. So they're gonna remove this one. They're gonna, so here, and they're gonna like somehow drag everything that was going into that cross gap through everything here and go back. So this is a kind of move that does not really help me finding short paths, from every cross gap. It's a very messed up move. So I'm not going to explain how we deal with it, but I'm going to give you a hint that this is where I use the Hanen-Halley-Pevsner algorithm. So And this is, so I use their algorithm to somehow make sure that I have dealt with all my separating rules at once, and I'm not creating new separating ones, okay? So, I think I'm done with the first problem. And just to tell you like about decomposition, there are not many decompositions that we know how to compute shortly. So there is the orientable one. The same approach that I just explained could be used just to reprove that thing with the same kind of bounds. And I can also prove the same approach decompositions of this form, where some part of it is like the non-orientable canonical and some part of it is like the orientable canonical. And that's it. Any other decomposition we don't know how to do. So now I'm going to move to the second problem, degenerate crossing number. So at first I'm going to talk about crossing numbers, but soon I'm going to move back to what I was just doing. So there are so many crossing numbers, as you probably know. The one I'm going to talk about is degenerate crossing number and genus crossing number. So Poch and Todt defined degenerate crossing number of a graph to be the minimum number of crossings among all the proper drawings of the graph, in which multiple crossings at a point are counted as a single one. So what is proper, I should explain. So these kind of crossings are not allowed. So an edge cannot pass through a vertex. Parallel crossings like this are not allowed, and self-crossings also are not allowed. And if three things are crossing like this, I'm going to count this as one crossing and not pairwise crossing. So they asked, so they defined this one, and Mohar said, okay, why not we allowing self-crossings? So he allowed self-crossings, and this introduces a genus crossing number, which I'm going to show by GCR. The degenerate crossing number I'm going to denote by VCR, don't forget that. And I'm going to tell you why he called it genus crossing number soon. By the definition, so I think it's clear that the genus crossing number is less than the degenerate crossing number for any graph. And there is a conjecture by Mohar that says that for every graph, actually these two are equal. Okay? Any questions?
So is the minimum necessary number for attaching cross cap for the drawing?
Tell me again. So the
So is it related? So if we try to draw the graph on the surface, maybe from the sphere, is it the minimum number or just need to attach the cross caps, or?
So here is just crossing number. I'm going to move to the cross cap and everything right now. I'm going to explain how these things are related, but so far it's just crossing number. You're just drawing your graph in the plane. Okay? And their edges are going to cross each
So
other.
when you cross, so let's say you have three curves intersecting at a single point.
Yeah.
Do you have to go in a like correct order, or like can I have? Is it possible to have a blue edge coming in and then I mean here it goes in the correct order, right? So
Like, okay?
you have a circular ordering.
Yes.
But is
So,
it okay
in case
to
you
not to
don't-
follow?
Okay, in case you don't have a circular ordering, it means that you're having
Oh,
some
I see. Okay.
So all my crossing, so everything would be crossing really nicely. Okay, so now let me tell you how everything is related to the things that I was just describing. So first, let me tell you, so the non-orientable genus of a graph is just the minimum number of cross gaps that you need to draw on that to draw that graph in a non-orientable surface. So Mohar proves that actually the genus crossing number is equal to the non-orientable genus of the graph, and it's pretty easy to see. So start with a genus crossing number. So imagine that you're given with a drawing on the plane with minimum, and you can like just replace every crossing with a cross cap, and then you get something. So this way you get one side, and the other one, if you have another, you know that the graph has an embedding of on, for example, with G cross caps, you get the cross cap drawing, and just that's it. So And that this is exactly why he called it genus crossing number.
So you don't need to think about the self-intersection?
Okay, now, so in the GCR, the genus crossing number, you are allowed to self-intersect, okay? So an edge can enter a cross-cap more than once. But this means that if you just want to consider the degenerate crossing number like this, you have to forbid edges to enter more than once, okay? So let's call a cross-cap drawing perfect whenever every edge is entering everything at most once, okay? And now Mohar's conjecture translates to this, that every graph admits a perfect cross-cap drawing with exactly the non-orientable genus cross-caps, okay?
Are these equivalent statements?
Yes, these two are equivalent. Yeah. Now, let me tell you about other conjectures of Mohar. Mohar has a lot of conjectures. So the first one is the one you saw. There is a stronger version of this conjecture that says every loopless graph embedded on a non-orientable surface admits a perfect cross-cap drawing. The difference between these two is that in the first one, the embedding of the graph is not fixed. You are given the graph, and you can just think about any embedding of this graph with minimal genus, okay? And in the second one, the graph is given with the embedding, and you want to find if you want to see if you can draw it perfectly. And there is a third conjecture that is even stronger than this one, in which he forbids the loops to be separating, and that's it. So, okay, now, obviously, conjecture 3 implies conjecture 2, and conjecture 2 implies conjecture 1. So it's pretty nice, but the conjecture 2 is wrong. And so Schaefer and Stefankovic have a counterexample that is surprisingly very small. It has one vertex, and even I think 5 loops. So this one is wrong by this example, and the second one is also wrong, and this is what we did. And our example has 2 vertices, so you can, yeah. So we prove that this conjecture is wrong. We find a counterexample. We also show that except 2 exceptional families of graphs, the graphs with 2 vertices and loopless, you can always find a perfect cross-cap drawing. So there are a very restricted amount of graphs that do not satisfy conjecture 2. Any questions?
Yeah.
Yes.
So the conjecture to the point why it's stronger is that you want that drawing to be on the same surface where you already embedded, or does it has the new embedding, the perfect drawing, has to have to do anything with the embedding that you already given?
So
I don't see it in.
No, okay. So the point is this. So when you have a graph, you can that example, for example, that the non-orientable genus pattern is 5.
Yeah.
Okay, but there are many ways to perhaps to embed it in the surface of genus 5. So here you're given the graph with a specific embedding.
Yeah.
And you want to find a cross-cap drawing. So cross-cap drawing is a little bit different than the embedding, right? So I told you that it's not kind of canonical. You can have different cross-cap drawings that correspond to one embedding.
Okay.
So here he asked if you can find a cross-cap drawing in which every edge is entering every cross-cap at most once, and the number of cross-caps is exactly the genus.
And the cross-cap drawing corresponds to exactly the given embedding.
Yes.
Okay,
Yes.
got it.
Exactly. Yeah. Yes.
Is there any, so in order to get these counterexamples, do you need at least a certain genus, or does it exist? Well, I guess.
The counterexample.
Do
So
they
I
have
think
them?
the genus of this one is 3.
Oh.
The genus of this one is 5.
Okay.
I mean, you can get as small as 5.
As small as 5,
Yeah.
I guess that
Yes.
Australian,
Yeah, yeah. Any more questions?
So does it implies conjecture 1 or still
No. So conjecture 1 is open. Conjecture 2 is somehow there is a bad example. So You don't know.
Well, conjecture one is open even for one vertex graph or something.
One vertex
So one-
graphs you can draw.
Yeah.
I don't know.
So one vertex graphs, since we're not fixing the embedding, one vertex graph can be drawn in the plane. So okay. So let's continue. So I'm not gonna explain the counterexample, but I'm gonna show it to you. This is the counterexample. So it's a two vertex graph. It's made somehow from two parts, the red one and the blue one here. So I have to mention that the bar means negative elements. So now this is a drawing with 5 cross gaps. That is actually the genus of this graph, the non-orientable genus of this graph. And as you can see, this red edge, that is 4, is entering these 3 cross gaps twice. Okay? And if you want to forbid this, we prove that actually you need 6 cross gaps. So this is a counterexample. And so this proves that the GCR is 5, but the DCR is 6. Okay? I can explain to anyone who's interested after the talk why it's worth and everything. It's pretty easy, not that complicated. So now I want to explain how the algorithm that allows us to get perfect cross-gap drawings. But before, let's go back to the sign reversal distance algorithm by Hanan, Halley, and Felsner. So if I just decided to attach every side to a vertex, then this would have been a 2-vertex graph embedding that is loopless, right? So one would ask, why isn't this enough? Because everything, like every edge is entering to every cross gap once with this definition of reversals and everything. The reason that this wouldn't work is that actually this algorithm does not use the same number of cross gaps or reversals, so it uses more. Okay, so these things that okay, so the minimum number of sign reversal distance is more than the non-orientable genus, as I said, and there are some elements that are responsible for these extra ones. These are something like this, which I call blocks, but they call hurdles. Okay. So okay, if I want to say what is actually a block, it's just any sequence that is somehow encompassed by 2 elements, for example 1 and 4, and everything has the same sign. Okay. And so, for example, if 2 and 3 are between 4 and 1 here, then 2 and 3 also have to be between 1 and 4 and nothing else. Okay. So these things are proved to be bad for their algorithm. So here, for example, the genus of this thing is 3, but their algorithm gives 4 reversals to sort this out. So, oh my god, so I forgot to tell you something, so I have to go back. So one thing that is in their algorithm, so they start at one permutation, then they add 1 cross gap at a time. So there is some order on the cross gap and some monotonicity. Okay, so here you can see the monotonicity. And I can show that I can deal with these hurdles in my topological setting if I just forget about this monotonicity and still keeping the property that everything is entered once, like every edge is entering every cross gap once. So this is the one, this is how I do it. So here 4 is entering these cross gaps. Let's say cross gap 1, 2, 3, but 1 is entering 3, 2, 1. So I forgot about the order, but I'm dealing with it with the right number of genus and everything is entering once. So let me tell you now about the algorithm. So the first thing that imagine that you're given with this graph, 2-vertex loopless graph, and the first thing is to reduce the scheme. So what does it mean? I'm going to search for blocks. So here the red one is 1 block and the blue one is 1. What I'm going to do is that, okay, so you can see that the elements here are positive and the elements here are negative. I'm going to replace each of them with just one like folded edge like this with the same signature. So so here it was positive, I'm going to replace it with X, and this one with the gray Y with the bar. Okay? I can do this until I have no more blocks in my graph, right? And then I know that the algorithm of Hanan, Halley, and Pevsner can solve this problem with the right number of cross gaps. So I use the algorithm to draw that. So here it was my reduced graph. And now I'm going to choose for each of my bolded edges one cross gap that they enter. So for X, I'm going to choose this. For Y, I'm going to choose this. And what I'm going to do to like bring back the edges is that I'm going to blow them up like this. So let's see. This is what's happening. So I'm going to blow each. For example, this one is blowing up to 3, which is the number of cross gaps that I need to draw the edges that I just reduced. And this like this. So I can continue drawing my edges like this. So this is how the algorithm works. And now, the only cases that I cannot use this algorithm for are graphs that reduce to one of these two forms. These two cannot be, I cannot use the algorithm. This is my counterexample. If you remember, there was like two parts, one positive, one negative. And this one, we didn't prove that it's actually a counterexample or not, but it cannot be drawn with this algorithm at least. So this shows that, in particular, under standard models of random maps, almost all two-vertex loopless embedded graphs satisfy conjecture, right? So it's just not true for these ones. So, any questions?
By standard map, you have 2 permutations.
Not two. You can just fix one of them to be
right.
identity. So it's just one permutation. Okay. So okay, it's not too good, but you can also generalize this to loopless bivertex graphs, with more vertices. For example, if your graph is like this, you can somehow find phantom edges to contract it to something that is 2 vertices. And you just have to be careful when you add these edges, you do not increase the genus, and that's it. So here I found this, I contracted, I find this and I contracted, and I'm ending up with a vertex case. So this is it. So for the conclusion, how much is it? Okay. So for the conclusion, so regarding the first problem, I have to say that Megami's conjecture is still open. It would imply that every decomposition, every shape of decomposition can be computed efficiently and shortly. Not efficiently, shortly, but it's still open. And Mohar's conjecture, the first one, is also open. And one thing that I want to mention, one observation here, is that there is still a good chance that this conjecture is true, because imagine that you're given with any embedding, and with the Schaefer and Stefankovic algorithm, you can get a graph drawing, a cross-gap drawing, in which every edge enters each cross-gap at most twice, right? For example, here, the red one. So in the case that you have more than 2 vertices, you can move this vertex here through this cross-gap. Okay, not this one, through this cross-gap, like this. And now you have the same, like a valid cross-gap drawing, but nothing is entering anything more than once. So when the number of vertices and everything increases, the chances are higher to find the perfect cross-gap drawing. So this is what I wanted to mention. And that's it. Thank you.
Thank you. Any questions?
Yes.
So, for that, to consider about algorithms, how you encode your graphical surfaces in the
Okay, so you remember I told you about the embedding schemes? Let me the rotation system and signature. So the one I told you was like for 1 vertex graphs. Where am I? This is not true. So the one I showed you was for 1 vertex graphs here, and for non-orientable surfaces you need these signatures to tell you about the sidedness of the curves. But you can have this for multiple vertices. Your edges still would have some signatures, but then there you have to look at the curves and like the sidedness of a curve would be the multiplication of the signature of the edges that it consists. So this is one of the ways to encode. Yes.
So if your embedded graph has like large face width, like can you get even shorter decompositions, like sublinear?
I'm not sure. Let me think. You mean, okay, sublinear, like order of
Like
what?
root n?
I don't think so. I'm not sure. But I think we can show that, for example, a random one face, one vertex embedded graph has super linear in G size. So yeah, that's the only thing I know about the lower bound.
So I wonder when we need many crossings. Do you have a specific example?
When we need many crossings.
In your main theorem, so we can bound the number of crossings by the constant number, but still the constants.
You're talking about the decompositions?
Yes.
Okay.
Yes.
Okay. I don't know if anyone knows that, but maybe there has to be some lower bounds. I don't know the lower bounds though, but it's not that. I mean, that's interesting. The lower bounds are like not interesting, kind of. Any more questions?
You
Okay.
have this number 30, right? The number of times it crosses, right?
Yeah.
Is there some example where you lower bound?
No. So that no. So we don't know about lower bounds, and actually this 30 is like probably you can do better. I mean, we're not really caring about optimizing this because only we cared about the asymptotics to be constant and everything. Yes.
If the graph that you're in that same, if the graph has many more edges, could you do better than G times n? So suppose that n is much larger than G.
Can you say again?
So you showed that for this canonical embedding, you
Yeah.
can get order G times n crossings.
Yes, in total, yes.
Yeah. Now, think about the case that n is much larger than G. Could you
Okay.
get a better dependence on n?
So let me think. I'm not sure if somehow you can like contract the edges of the graph to somehow make it more dependent on like G,
I see.
but I'm not really sure. Let me.
Are you allowed parallel edges? Are you allowed to have parallel edges?
You are allowed to have parallel edges, yes.
Then I guess you can't.
But what do you mean by parallel? Like, because if they are homotopic, they're kind of not very interesting. They can just.
They're not very interesting, but they
Yeah.
would sort of trivially force you to
Okay.
scale, right?
Okay.
The
N is
number
here,
of
n is the
Yeah,
number
but-
of edges.
Yeah, but if I just
Put
create
all-
parallel copies of
Yeah,
the
but the-
edges, then what have you done? for
Okay,
your
yes,
graph?
yes, yes,
That's-
yes.
it's gonna
So,
scale.
yeah, we're.
If
So
this is
it's-
allowed. But if you're not allowed homotopic edges, then maybe you could still.
Yeah, but topologically, it's not very interesting. So, kind of. Okay. Any more questions?
Any more questions?
Vertices might make it easier. So do you have perhaps a weaker version of the conjecture that uses this idea?
I would say no.
Yeah, I don't know what exactly how to formalize
Yeah.
the case that might come easy with this.
Yes.
So what is known about this Mohar's conjecture? How far apart can? Is there some bound on how far apart the two crossing are? The conjecture
no.
to be equal, right?
Yes.
One is by
Yes.
definition smaller than the other.
Yes.
Is
I
there-
think so. I think the best thing we know by Schaefer and Stefankovic again I think they bound DCR by 6 times DCR, something like that.
Okay.
So, no more questions? Really? Okay.
I can ask more questions. What do you-
Okay, go ahead.
So in that setting, the bound is like 6 times. Would it be possible to like weaken the both stronger conjectures by saying, okay, we don't get a quite perfect cross-cap drawing, but we can bound the number of times something goes through a cross-cap? Is that realistic, or do the counterexamples
So,
admit like arbitrarily bad, non-perfect?
But how much do you want to allow for the edges to enter a cross-cap?
Yeah, that's what I'm asking.
So-
Can the counterexamples be generalized
So
to
we
be
know that
arbitrarily
you
bad?
can always embed it with edges entering cross-caps twice at most, like everything. So this is
So even if I can give an embedded ground?
yeah.
Okay.
Yeah. So twice is, we know that you can always get twice with this genus. Yeah.
Did you think about using the mapping class group? Because the topologists know the generators for the mapping class group, so you can just
Yeah, I would
use the
say
rules.
I didn't think about it because I don't know it.
we can help.
So, okay.
All right, I think we should